1.3.1, you can see the first subtopic here, electronegativity. So first let's understand what is electronegativity. So you can see here, electronegativity is the ability of an atom to attract a pair of electrons towards itself in a covalent bond. So first of all, you need to understand that a covalent bond must be formed first. Okay, covalent bond must be formed. So let's say, for example, I take a covalent molecule like HCl. So they form covalent bond here, and then the bonding electron is here. But the thing is, the bonding electron is attracted more towards the chlorine. Okay, chlorine attract the electrons more. So because chlorine is more electronegative. So that is how we can see the difference in electronegativity between hydrogen and chlorine. So chlorine is more electronegative, so chlorine attract the bonding electron toward itself more compared to hydrogens. So this phenomenon arises from the positive nucleus ability to attract the negatively charged electrons. So that means the chlorines, the nucleus of the chlorines attract the electrons more. Okay, so that's why it is attracting the bonding electron towards itself. So the Pauling scale is used to assign the value of electron negativity for each atom. So you can see the information down
Wait,
here.
I thought HCl was ionically bonded.
HCl. HCl.
Yeah.
HCl. Oh, you thought this is a ionic compound?
Yeah, because I thought hydrogen is like positive ion.
Oh, okay. So if you want to understand whether this is ionic or covalent, right? So basically there is a rule. There is a rule. So how we find out whether they are ionic or covalent? So you look at the Pauling scale, right? You minus them. You find out the difference. Okay, you take chlorine 3.0, the scale here, 3.0 minus 2.1. Minus 2.1. Okay, so chlorine 3.0 minus 2.1. Okay, so 3.0 minus 2.1, so of course you get 0.9. Okay, so if you get 0.9, then is it covalent or ionic? So that is a way to determine. So I let you see another information. Okay, so there is a rules actually. I try to find it out. Okay, so let's look at the difference here. Okay, I write down the difference. If the difference of electronegativity is less than 0.5, that is non-polar covalent. Non-polar covalent. And then just now less than 1.6, right? So that is polar covalent. And then if the difference is greater than 2.0, that is ionic. So if you are not very sure, then you can use this as your general guidelines. So you can see the difference is kind of small, so it is under polar covalent. So they are covalent molecule, but they have polar bond. So we will come to polar bond later. So basically it is where the chlorine is delta negative, the hydrogen is delta positive. So that is what we call polar. Okay, so that's why the Pauling scale here is kind of important to see the difference of electronegativity to determine whether at the end they are covalent or ionic. So we can determine that. Okay, so if you want to know more, right, so I can give you one more example. Let's say, for example, this is kind of famous one. Aluminium chloride is covalent. It's covalent. Okay, so maybe you feel like, oh, this is metal and non-metal, but this is covalent. Okay, have you heard before? This is covalent?
No.
No, huh? Okay, so you see 3.0 minus 1.5, so that is 1.5, so it's under this covalent. Okay, so but we can't say that aluminium always form covalent. So aluminium form ionic also. For example, let's say aluminium oxide. So aluminium oxide. So you can see the difference. 3.5 minus 1.5, so you get 2.0, 2.0 is just nice, so it is ionic. It's ionic. So this is the special examples that you need to know about that. So let's move on. We look at the next page. So on this page, let's see. They say fluorine is the most electronegative atom on the periodic table with a value of 4.0 on the Pauling scale. So 4.0 is the highest. It is best at attracting electrons density towards itself when covalently bonded to another atom. So you can see this is the bonding electrons. So this is very electronegative. The bonding electron is not shared in the middle. It is more towards the fluorine. So because fluorine is more electronegative than carbon, so both electrons are attracted towards the fluorine. And then you can see here the shared pair of electrons in the CF bond. This is the shared pair. So making fluorine to be delta negative and carbon to be delta positive. So let's move on. Okay, here electronegativity affecting factors. So the first factors that affect electronegativity is the nuclear charge. So nuclear charge means the charge due to because of the protons, nuclear charge. Attraction exists between the positively charged protons in the nucleus and negatively charged electrons found in the energy levels of an atom. So that is nuclear charge. Nuclear charge is the charge, the attraction between proton and electrons. So an increase in the number of protons leads to an increase in nuclear attractions for the electrons in the outer shell. So you can see example here. Sodium, magnesium, aluminium, more and more protons. So when there are more and more protons, then the attractions of electrons is getting greater and greater. So it is shown by the value here, 0.9, 1.2, 1.5. So this is greater in attracting the electrons. So therefore, an increased nuclear charge results in an increased electronegativity. So this one has greater electronegativity because of greater number of protons. So we look at this factor now. This is the second factor, atomic radius. Okay, so the information here, they say the atomic radius is the distance between the nucleus and electrons in the outermost shell. Okay, so it is from the center of the nucleus to the electrons in the outermost shell. Okay, so that is the atomic radius. So let's say, for example, let's say if you have sodium, so 1, 2, 3, 3 shell, okay, 2 electrons, followed by 8 electrons in the second shell, followed by 1 electron. Okay, so atomic nucleus from the center where the atomic radius is here to here, the blue one. Okay, so electrons closer to the nucleus are more strongly attracted towards its positive nucleus. So that means this electron is more strongly attracted compared to this electron. This electron is further away, so the attraction is weaker. So those electrons further away from the nucleus are less strongly attracted towards the nucleus. So this is less strongly attracted. So therefore, an increased atomic radius results in a decrease in electronegativity. So because it is far away, right? So it affects the electronegativity in the opposite way. So the greater the radius, the smaller the electronegativity, because it could hardly attract when it is too far. Okay, so the second factor. Now let's move on. This one. Okay, so the diagram here shows what I explained just now. So you can see atom A has the smaller radius, atom B has a greater radius. So you should expect atom B to have lesser electronegativity. So that's why you can see here atom A to have a higher electronegativity. So this is higher in electronegativity because the radius is small. This is smaller in electronegativity because the radius is big. So that's the relationship. Now we look at the third factor, which is called shielding. Okay, shielding. Few energy levels can shield or mask the effect of the nuclear charge, causing the outer electrons to be less attracted to the nucleus. Okay, so that means, let's say example, I use sodium again. So sodium, sodium has 2 electrons followed by 8. 1, 2, 3, 4, 5, 6, 7, 8, followed by 1 electron here. So the nucleus stay in the middle. The nucleus, if this nucleus is going to attract the outermost electron, there is a problem. The problem is it is blocked by inner electrons. That is called shielding. Okay, so to attract that is not that easy. It's not that easy because the electron at the outer shell is at the same time repelling the electron at the outer shell. Okay, so these electrons at the inner shell is repelling the electron at the outer shell. So it makes the attraction by the nucleus hard to happen. Okay, so that is called shielding. So therefore, the addition of extra shells and subshells, so as long as you have more and more shell, right, then shielding is getting greater and greater, will cause the outer electrons to experience less of the attractive force of the nucleus. So hard to attract now because of the shielding effect. Okay, so there are 2 shells that make shielding effects to be great. So you see sodium has higher electronegativity than cesium. Cesium is period 6. So period 6 is where it has 6 shells. 6 shells. Imagine they are big in size, 6 shells altogether. As it has fewer shells. So sodium has fewer shells, just 3. But cesium has 6. So shielding effect is very big in cesium. So then the attraction is, the electronegativity is hence small. So they cannot attract the outermost electron that much already for cesium. So as it has fewer shells, and therefore the outer electron experience less shielding than in cesium. Okay, so they are trying to say that sodium has less shell, then less shielding, then greater electronegativity compared to cesium. Okay, so now here, thus an increased number of inner shells and subshells will result in a decreased electronegativity. So opposite effect again. So increase in shielding, then decrease in electronegativity. So same situation like atomic radius, opposite effect also. The greater the atomic radius, the lesser the electronegativity. Okay, so we have three factors so far. Now let's move on. Okay, so this is the picture that explained the shielding just now. So as you can see, this is one shell. Okay, one shell has strong attraction because the nucleus can directly attract the electrons. This one has two shells, so you can see two shells, the red one and the green one. So there is one few electron shell to mask the nuclear charge. So that means this one is trying to block the attractions, trying to block the attraction of the nucleus towards the outermost electrons. And this one is even more shielding because there are one, two, three shells. So the two inner shells is trying to block the attraction of the nucleus on the outermost electrons. So there are greater shielding effect for this case. So now let's see exam tips. The nuclear charge, atomic radius, and shielding are all linked to each other. As nuclear charge increases, the nucleus has a greater attractive force on the electrons in shells, given that the shielding doesn't increase. Shielding doesn't increase if they are at the same period. At the same period, so normally the the change in the shielding effect is nothing there if the elements are all stay in the same period. So for example, like period 3, so we have sodium followed by magnesium, followed by aluminium, followed by silicon, followed by phosphorus, sulfur, chlorine, and okay, let's say until here only lah. So what can I say is they all have three shells. Okay, and they all have three shells. So if they all have three shells, basically their shielding effect is more or less the same, but the nucleus is getting more and more, and because of that the attractive force is getting greater and greater, and because of that the electron negativity should be greater and greater. Okay, so and as a result of this the atomic radius decreases. So you can see also the atomic radius should be smaller and smaller for this case. Okay, now let's move on. Electronegativity trend. So let's see the trend here. Okay, so they say electronegativity varies across periods and down the groups of the periodic table. So down a group, so you can see hydrogen, lithium, sodium. So their size is getting bigger and bigger. Okay, you see how is the change in electronegativity. They said electronegativity decreases going down a group. Decreases. So why decrease? Because the number of shells increases. This one shell, this one two shells, this one three shells. Okay, this one sodium has three shells. So when they have more and more shells, they have more and more shielding. Then the atomic radius increases. Okay, you can see the size. Yeah, increase in atomic radius. Increase in nuclear charge is negligible. Okay, so although there are more and more protons, so supposed to have more and more nuclear charge at the same time, but we ignore this. Okay, we ignore this because whenever shielding effect is there, shielding effect will overcome the nuclear charge factor. So this is a bigger factor, this is a greater factor. It affects more compared to nuclear charge. So if you have more and more shells, then you have to say that the shielding play a major role here. Nuclear charge is playing just a minor role. So less attraction. So the final effect is less attraction because of more shielding, less attraction between nucleus and bonding electrons. Okay, so from the statement here, so you remember, shielding is the major factor, but the nuclear charge is just the minor factor. So when there is an increase of shielding effect as well as the increase of nuclear charge, then we have to say that attraction is getting lesser, as in here. So when both of these increase, so the final effect is less attraction, because the major factors is shielding, which causes less attraction. Okay, now let's see here. There is a decrease in electronegativity going down the growth. Decrease in electronegativity means less attractions towards electrons. And the second point, the nuclear charge increases as more protons are being added to the nucleus. Okay, so there are more and more protons, but don't forget, nuclear charge is the minor factor. However, each element has an extra filled electron shell, which increases shielding. Shielding is the major effect. The shielding here make repulsion of electrons greater rather than attractions. So the addition of the extra shells increases the distance between the nucleus and the outer electrons, resulting in larger atomic radii. So you can see the atomic radii is getting larger. Okay, so you see they're talking about the three factors, nuclear charge, shielding, and the atomic radii. So overall, there is decrease in attractions between the nucleus and the outer bonding electrons. So that's why electronegativity decreases. Okay, so let's move on. Across the period, okay, let's see what happened. We look at the picture first. So going across the period, electronegativity increases across the period. So this is the example. This is period 2, lithium, beryllium, and so on until fluorine. So electronegativity increases. Okay, so reasons: nuclear charge increases. So atomic radius decreases. Shielding is not affecting much here because they have the same number of shells, which are 2 shells, so shielding is not there. So the major factor is not playing the role, then the minor factor is affecting. So the minor factor, which is the nuclear charge, right, is now affecting the electronegativity. So there are more and more protons, then the attraction is getting greater and greater. So electronegativity is getting greater and greater. So greater attraction between nucleus and bonding electrons. So you can see here, the nuclear charge increases with the additions of protons to the nucleus. So this one is 3 protons, then 4 protons, and keep going until 9 protons. Okay, so the nuclear charge increases across the period. And then shielding remains reasonably the same across the period as no new shells are being added to the atoms. So shielding is very much affected by the shells. So if there is no change in the number of shells, so basically the shielding will remain more or less the same. Okay, then the next point, the nucleus has an increasingly strong attractions for the bonding pair of electrons of atoms across the period of the periodic table. So shielding is not playing the role here, and the nuclear charge is playing the role, and because of that, the attraction is increasingly strong. Okay, so and it make the attraction greater, and then electronegativity increases. So this result in smaller atomic radii. So smaller atomic radii. Smaller atomic radii means greater electronegativity. So they are trying to relate the three factors in this way. So when you look at the explanation here, so remember three keywords. Nuclear charge, how is it? Increase. Shielding, how is it? Same. Atomic radii, how is it? Smaller. And then you can conclude that the electronegativity increases. So three factors: nuclear charge, shielding, and atomic radii. Okay, let's move on. Trend down a group and across a periodic table. Okay, so now down a group, nuclear charge increases, shielding increases. So this is major factor like what I said. So when both are increasing, so at the end you have to use shielding as the major factors. Shielding will make repulsion happen. So and then atomic radius increases because of the shielding, and because of the big size, then the electronegativity decreases. So the trend is you talk about this factor first, then this followed by this, and this one will affect this. If this one's big, this one's small. If this one's small, then this is big. So across the period, so first we said nuclear charge increases, shielding's constant or same because of the same number of shells, and because of now this is not playing the role here, so the nuclear charge is attracting and making it small, making the atomic radius to be small. Then when this is small, this is big, electronegativity increases. Okay, now exam tips. Remember, the general trend is an increase in electronegativity towards the top right of the periodic table. That means in your periodic table, right? So the one on the right, fluorine, is the greatest in electron negativity. Just ignore the noble gases. So on the right, the top one, fluorine, is the champion in electron negativity. So fluorine is the most electronegative element in the periodic table. Okay, so now let's see the effect of electronegativity in the bonding. Okay, so you can see here, electronegativity predicting bond formation. The differences in Pauling electron negativity values can be used to predict whether a bond is covalent or ionic in character. So like what I said just now, if the difference is greater than 2, then it is ionic. If it is less than 2, 1 point something, then it is polar covalent. Then if it's 0 point something, then that is non-polar. Okay, so the difference will affect the bond. So single covalent bonds are formed by sharing a pair of electrons between two atoms. In diatomic molecules, the electron density is shared equally between the two atoms. So you can see this is diatomic molecules. So where the two atoms here are the same atom, and same atoms. So if they are same atoms, right, the shared electrons are equally shared. That means it's something like this. It stay in the middle. Because these two have the same strength in attracting the bonding electron. So at the end, they just share in the middle. So both atoms, you have the same electron negativity value and have an equal attraction for the bonding pair of electrons, leading to formation of a covalent bond. So covalent bond, right, if you still remember, right, the idea is they share electrons. So they are sharing electron perfectly here. This is the perfect situations of sharing electron. You want to share, you put the electron in the middle, so that is fair. So that is why this is the pure covalent, and it is also known as non-polar molecule. Non-polar, that means we don't have delta plus delta minus, we don't have that, as this is
Oh,
equally
okay.
shared. Yeah, that is non-polar. Okay, so let's move on. Electronegativity and ionic bonds. Okay, so let's see the information here. So they say when atoms of different electronegativities form a molecule, the shared electrons are not equally distributed in the bond. For example, H and F. H and F, this is very electronegative. So the attraction towards the bonding electron is very much greater compared to hydrogen. So that's why the bonding electron is more towards the fluorine, and it makes here more negative. So that's why there is a delta minus here. So this is delta positive because it doesn't get the electrons. The electron is very far away, and hence this is positively charged, slightly positively charged. Okay, so let's see. The more electronegative atom, the atom with the higher value on the Pauling scale, will draw the bonding pair of electrons towards itself. Okay, so this is the case. Molecule with partial charges forms as a result. So they form polar molecule, polar covalent molecule. Polar covalent molecule. The difference is 1 point something, you see, 1 point something, 1.9. Almost ionic already, this one. Almost ionic. So it's polar covalent molecule. So the more electronegative atoms you have partial negative charge, as in fluorine, we call it delta negative. The less electronegative atom will have a partial positive charge, as in hydrogen. So this is delta positive. Okay, so at the end we call this polar covalent molecule. So polar covalent molecule happens on this hydrogen fluoride. Okay, let's move on. Okay. If there is a large difference in electronegativity of the two atoms in a molecule, the least electronegative atom's electron will transfer to the other atoms. So it is transferring now. Okay, you see the difference is too big. 4.0 minus 1.0 is 3.0, so greater than 2 a lot. So if that is the case, they will form ionic compound. And ionic compound, they use transfer of electrons. They are not sharing. It is totally given to fluorine. So that's why it become negatively charged, and this become positively charged. They form anion and cation. So that is ionic bond. So ionic bond is formed when the difference in electronegativity is too big, greater than 2. So equal to 2 is just fine. Okay, so greater or equal than 2, then it is ionic. So one atom transfer its electrons and the other gain that electron. Okay, so this one donate electron, this one gain electron. So that's why this is negatively charged, this is positively charged. We don't use delta minus, we use minus straight away. We don't use delta plus, we use plus straight away. So we call it cations for the positive charge species. It's the one that lost an electron. And the anion is negatively charged. It's the species which has gained an electron. Okay, so this is the situation. And now let's see Okay, this table is good enough as our reference. So greater than 2, ionic, ionic 1.0 to 2.0 polar covalent, I just realized that just now our example, right, aluminium oxide, which is exactly 2.0 in exam aluminium oxide is known as ionic. It's known as ionic. So just be flexible with this table, so 2.0 is ionic in past paper, so we follow past paper of course, because we sit for exam, right? So 2.0 ionic, then 1 point something polar covalent, 0 point something non-polar covalent. So this is a table that will be easier for us, so 1 point something, this is 2 point something, this one is 0 point something, so it's basically 0 1 2. Okay, so let's move on. Okay, so we finish electronegativity at the end. We don't have much question on electronegativity alone, so they will ask together with something else, so we have to keep moving. So let's see. Ionic bonding definition. As a general rule, metals are on the left of the periodic table and non-metals are on the right hand side. So that is the general rules in periodic table. And ionic bonding involves the transfer of electrons from a metallic element to a non-metallic element. Okay, so transfer of electrons happen, not sharing, it's transferring. So transferring electrons usually leaves the metal and the non-metal with a full outer shell. So that means after transferring, the metal will have full outer shell, the non-metal will also have full outer shell. So example, let's see the picture here. So you can see lithium. Lithium is basically 2 electrons at the inner shell and 1 electron at the outer shell. So after transferring, so the electrons at the outer shell contains no more electrons, and then the electron at the inner shell is full. Okay, it's full, full with 2 electrons, 1s2 basically. Okay, so another example is like chlorine. So imagine chlorine is 287. I write this way because this way is fast, so by right you have to write 1s2 to s2 and so on, so when they form chloride it becomes 288. So again, when transferring of electron happens, at the end they are having full outer shell, full of electron, which is 8 electrons for this case. Then metal lose electrons from their valence shell, so this is the example, and then forming positively charged cations. Non-metal atom gain electrons, forming negatively charged anions. So this is the example, gain electrons, become negatively charged anion. Once the atoms become ions, their electronic configurations are the same as a stable noble gas. So for example, a potassium ions, when they form K+, they have 288. A chloride ions, when they form Cl-, they also have 288. So they have the same electronic configuration as in the noble gas. Okay, and let's look at the picture on the next page. Okay, so you can see it here. This is the non-metal, so oxygen. So oxygen has 6 outer electrons. So oxygen tend to gain 2 electrons to form the full outer shell of 8 electrons here. Okay, so that's why it takes 2 minus. After gaining 2 electrons, it becomes 2 minus. Okay. Now, cation and anions are oppositely charged and therefore attracted to each other. Okay, so attracted to each other. That is how the ionic bond is formed, is because of the attraction between the positive ion and the negative ion. So we call this attraction as electrostatic attractions. So it's between the positively charged ion and the negatively charged. We call it electrostatic attractions. So formed between the oppositely charged ions to form ionic compounds. The ionic bond is the electrostatic attractions formed between the oppositely charged ions, which occur in all directions. This form of attraction is very strong and require a lot of energy to overcome. This causes high melting points in ionic compounds. Okay, so it is strong. So that's why ionic compound that has high melting point, because the ionic bond is strong. Okay, so one highlight here, you will see no metal and non-metal in ammonium chloride, but this is ionic. So this is ionic, because this is ammonium ions that stick to chloride ion. So this is ionic. Okay, so let's see the next one. Okay, here what we can see is the formation of ionic compound. So you can see potassium has 1 valence electron, chlorine has 7 valence electrons. So to form ionic compound, the potassium had to give the electron to the chlorine. So potassium losing 1 electron become positively charged. Chlorine accepting 1 electron become negatively charged. Now they attract each other and they form the ionic compound. Okay, so we draw like this, when they ask you to draw the ionic compound, we draw like this. Okay, with a square bracket and the charges. Okay, let's move on. Okay, let's see. The ions form lattice structures, which is an evenly distributed crystalline structures. So this is the lattice structures. What happened here is they want you to understand that, let's say for example, sodium chloride, where this is sodium positive, this is Cl minus. Although when we write NaCl, but it doesn't mean that it is just 1 sodium and 1 chloride. In actual situation, there are so many sodiums and so many chlorides that are present in the structures. They are like arranging themselves in alternate. So for example, right, you see here the blue dot is positively charged ions. Imagine it's sodium ion. So sodium ions, right, let's say the middle one, it is surrounded by chloride. You see the green one is negatively charged ion. Chloride is forming covalent bond with sodium on the left, right, front, back, up and down, so there are 6 ionic bonds over there, which form with 1 sodium. So likewise, when you consider chloride, there are 6 sodium which are staying, which are forming ionic bond with this chloride. So one is on the right, another one on the left, front, back, up and down. So altogether 6 sodium ion that are forming ionic bond with 1 chloride ion. So this is called the coordination number. So where the coordination number is 6, because they are having 6 direct neighbor. Okay, 6 direct neighbor, so that is coordination number. But we don't really want to know about coordination number in details, so you just need to roughly know that coordination number is how many direct neighbors that can form ionic bond with the ions. So it is 6 for sodium and 6 for chloride. Okay, now this point, ion in a lattice are arranged in a regular repeating pattern so that positive charges cancel out negative charges. So they are repeating, as in here. The attraction between the cation and anion is occurring in all directions. So that's why you can see they are on the up, down, left, right, front, back to attract the oppositely charged ions. So each ion is attracted to all of the oppositely charged ion around it. Therefore, the final lattice is overall electrically neutral. Okay, overall neutral. So this is the lattice. Okay, so what is important in exam? Let's see here. Metals usually lose all electrons. You see they use usually. So from their outer valence shell to become cations. Okay, so it is not metal that form cation all the time. So ammonium can form cation as well. So you can make use of the groups of on the periodic table to work out how many electrons on atoms is likely to lose. So for example, group 1, how many electrons are they going to lose? What do you think?
1.
Yeah, 1 electrons. So they are forming ions of positive 1. Okay, so group 2, how many electrons?
2.
2 electrons. So they form cation of 2 positive. Then the next one is group 13. Group 13, how many electrons then? 3 electrons.
3.
Yes, 3 electrons. So group 13, for example, aluminium. So it loses 3 electrons, then they form aluminium 3 plus. Okay, and then the other thing is the non-metal. The non-metal. So let's say non-metal, I put it here. In general, group 15, group 16, group 17. They are non-metals. So first, we need to know that group 15 already have 5 valence electrons. So there are 5 valence electrons, 6 valence electrons, and 7 valence electrons. So in general, it's like that. So group 15 tend to receive electrons rather than donate electrons. Donate electron is a bit hard because a lot to donate, it has to donate 5 electrons to make it fully filled. Okay, to make the inner shell fully filled. So donating 5 is not possible, but receiving 3 is easier for group 15. So receiving 3 electrons. This one receiving 2 electrons, receiving 1 electron. And because of that, right, the charge is 1 minus, 2 minus, and 3 minus. Okay, so they become cations, and this become anion, then they attract each other, then they form ionic bond. So the electrostatic attraction between oppositely charged ion is the ionic bond. Okay, let's move on. Ionic bonding examples. Okay, so the first example, sodium chloride. Okay, so sodium, group 1, is a metal. So group 1, the cation is positive 1. chlorine, group 7 or group 17, so group 17 is better lah for A level. So group 17 gains 1 electrons, and then the charge is -1, is chloride. Okay, so they become oppositely charged, and then they are attracting each other by electrostatic forces to form NaCl, and the charge cancel off, and at the end they are neutral, and NaCl are neutral. So this is the picture. One balance put here become positively charged, and then 8 electrons. So this one get 1 electrons and become -1. So NaCl is formed. Okay, let's see another example. Magnesium oxide. So first we need to know that magnesium is group 2. Group 2, 2 plus. Oxide, group 6 or group 16. Group 16 is better. So gain 2 electrons, become 2 minus. So 2 plus, 2 minus, just nice. They can just cancel off their charge, and they attract each other through electrostatic forces. Then they form MgO as the ionic compound. So they are neutral at the end. So this is how it works. 2 electrons from magnesium come here, and they form the ionic compound. Okay, so MgO is the formula at the end. Now let's move on. Calcium fluoride. Okay, so you can see calcium group 2 form 2 plus, and then fluorine group 17, they're non-metal. They will gain 1 electrons, form fluoride. The charge is 1 minus. Okay, and then be careful with the charge. Charge you write 2 plus. Charge you write 2 plus.
Okay.
Oxidation you write +2. So charge 1 minus, oxidation number -1. Okay, then after that, the charge is not same over here. So because of that, you need to use 1 calcium and 2 fluoride to cancel off the charge, and hence the ionic bond, the ionic compound has formula CaF2. CaF2 is neutral in charge. Okay, so that's why 1 calcium have to form covalent bond with 2 fluorine, and this is the final diagram. So calcium become calcium 2 plus. So 1 electron is given to this fluorine, another electron is given to this fluorine. So this is fluoride, minus, so they cancel off. 2 plus and 1 minus and 1 minus at the end cancel off and form the ionic compound.